In this video, we're going to look at how we can control enzyme activity. And there's two major ways that you can control enzyme activity. One is that you control how much enzymes are actually available inside the cell. So you can either increase or decrease the rate of synthesis of enzymes, or increase or decrease the rate at which you destroy enzymes. But the other way to control enzyme activity, which we're really going to focus on in this video, is by modifying their catalytic activity through inhibitors or modulating their structure, and this uses what are called allosteric mechanisms, and that's mainly what we're going to focus on. Allosteric basically means you're binding not a substrate, but you're binding something that is affecting catalytic mechanisms. It's speeding it up or slowing it down. And usually when you bind a substance allosterically, you're not binding it at the actual site where you do the chemistry. You bind it somewhere else. And for our model system, we're going to look at aspartate transcarbamoylase, our ATCase, to look at our enzyme activity through allosteric regulation. So just to show you the mechanism of aspartate transcarbamoylase, it makes N-carbamyl aspartate from carbamyl phosphate and aspartate. This is the first step in making your pyrimidines. Now it can be allosterically inhibited, that means slowed down, by CTP, or allosterically activated, that means sped up, by ATP. Now if we look at the kinetics of this ATCase, the purple line here is if you do not have ATP or CTP. So no allosteric effectors are affecting your rate. If you look at this curve, it's sigmoidal, which means that we have cooperative binding here, similar to what we saw in hemoglobin. So that means ATCase has multiple binding sites for one enzyme, so multiple products are being created at a time. Now, if we give ATCase ATP, our curve shifts to the left. That means our enzyme is speeding up, or it takes less substrate to go faster. While if we give ATCase CTP, this enzyme slows down. It takes more substrate now to go faster. So that's what we're talking about with activation, which ATP, and inhibition, CTP. Now CTP is actually feedback inhibition. So ATCase will make N-carbamyl aspartate, and 6 enzymes later, 6 reactions later, you will eventually make CTP. Now, if you make enough CTP, CTP will go back to the first enzyme in the process, which is ATCase, and inhibit this enzyme, therefore inhibiting all of these steps. So the logic is, I have enough pyrimidines if I have CTP around, so please inhibit the first enzyme that makes pyrimidines. This is called feedback inhibition. And it will continue to block ATCase until the levels of ATP and CTP are relatively the same. On the other hand, if we have a lot of ATP, that means we have a lot of energy inside the cell. Let's start using that energy to make biomolecules. So if ATP is high, we will synthesize pyrimidines nucleotides. So we'll turn on ATCase to make our pyrimidines until the concentration of ATP is equal to the concentration of CTP. Now ATCase has two states, just like hemoglobin, has a T state and an R state. So T is inactive, R is active. Since R is active, it makes sense that ATP binds to the R state and CTP binds to the T state. Now, to understand how this enzyme works, what somebody has done is that they took a substrate analog, that is a substrate that looks like the actual substrate but it's slightly different. And this analog can bind, but it won't do the chemistry. So it's almost like an inhibitor, so we can see how this enzyme works. And what you find is that your analog, which looks like your actual substrates, will bind to the R state, but not the T state. So this is how we know the R state is the active state, or what the R state looks like, rather. Now, I said that this enzyme is cooperative, so to be cooperative, it needs multiple binding sites. So this actually has 5 different catalytic subunits, or sorry, 6 catalytic subunits. And so what happens is when you bind your carboxyl phosphate, which is this orange, in aspartate, you have a large conformational change. Some residues are moved up to 8 angstroms, which is a big move. And binding causes these tertiary and quaternary shifts, and so you are shifting every other binding site into the R state. So this is like the same idea we had for hemoglobin, where hemoglobin binds one molecule of oxygen, the other molecules of oxygens are going towards the R state. Here we bind carboxyl phosphate aspartate. Our other binding sites are going to the R state as well. Now, for ATP and CTP, we are actually binding roughly 60 angstroms away from the catalytic site. So way, way far away from the catalytic site. So that's why it's allosteric regulation. We're not binding at the binding site to modify activity. We're binding away from the binding site, which will lead to tertiary and quaternary changes. So CTP is an inhibitor. So it binds the T state. But if it does bind the R state, this binding will create large changes, which will shift everything to the T state. While ATP wants to be bound to the R state, so if ATP does bind to the T state, it will shift everything to the R state, which will increase the catalytic activity. So this T and R that we've seen with hemoglobin and now ATCase, you can apply that idea to many different enzymes where you have an on enzyme and an off enzyme. And these can be modulated by binding to something or by actually affecting the amino acids inside the enzyme. And speaking of that, most enzymes are actually modified by a covalent modification. And the big type of covalent modification is phosphorylation. There's other types, but phosphorylation is probably the most prevalent. In fact, 30% of all human proteins are subject to this reverse phosphorylation. And the amino acids that are going to be phosphorylated are serine, threonine, and tyrosine. And that's because you have an OH here, and you need that OH to be phosphorylated. The example we're going to look at is glycogen phosphorylase, which converts glycogen to glucose 1-phosphate, which is one of the first steps in breaking down glycogen to get energy for glycolysis. So we're going to look at that in our model system. So glycogen phosphorylase has 2 different forms. It has a phosphorylated form and dephosphorylated form. So the phosphorylated form is phosphorylase A, which is on the right here of this picture. The dephosphorylated form is phosphorylase B, which is on the left side of this image. Each one of these forms has 2 different states. You have a T state and an R state. So overall, you can have 4 different conformations of this enzyme. Phosphorylated in the R state, phosphorylated in the T state, unphosphorylated T state, unphosphorylated R state. So if you become phosphorylated, so during phosphorylation, serine 14, so you put a phosphate on serine 14. This will overall promote a T to R transformation. So basically, in phosphorylase B, you are much more likely to be in the T state than the R state. When you become phosphorylated, you become phosphorylase A. Now you're much more likely to be in the R state. That's why these arrows here are much darker. They're showing preference. Phosphorylase B prefers to be in the T state. Phosphorylase A prefers to be in the R state. Now we do have allosteric regulation of this enzyme as well, G6P. So G6P and ATP will go and it will bind phosphorylase B and it will favor the T state. And that's because this enzyme is one of the enzymes that go through glycolysis. And glycolysis will produce ATP, and one of the first steps of glycolysis is to make glucose 6-phosphate. So if you have a lot of energy or a lot of glucose 6-phosphate, you do not want to break down glycogen because glycogen is one of your energy storages. So this is feedback inhibition, allosteric regulation, saying do not break down glycogen anymore, go to the T state. While AMP means you are low energy. So if you have AMP around, you can actually activate phosphorylase B now. It's saying we need energy, please go to the R state. And for phosphorylase A, glucose will inactivate phosphorylase A because again, glucose is what you need for glycolysis. So if you have glucose available already, do not break down your energy storage to make glucose. That's the logic behind these enzymes. And that's it for this video. I will see you in the next video.